we've seen that when a substance undergoes a phase change, the amount of energy that's required is going to depend only on the mass of that substance, how much of it that there is, and then some constant that we call the heat of vaporization. In this experiment, we're going to try to determine what should be the value of that constant for water. So we're starting this experiment out. Got a scale here, and I'm going to put on a 150 milliliter beaker and zero it out. And my intention is to put about 100 grams of water in here. So there's 100.08 grams is the mass that I ended up with. Now I have another beaker on here, and you can see that this beaker is identical in mass because when I set it on the balance it still reads 0. My intention is to put about 5 grams of water in this beaker. And I got 5.02 grams, so pretty close to what I was shooting for. Now I'm going to put both of these beakers on the same hot plate. I'm putting them pretty close, as close as I can, to be in the same spot on the hot plate. And then I'm going to move my computer in here. This is attached to a temperature probe, and the temperature probe is going to be able to measure the temperature of the larger amount of water. So that's going to be in the screen so we can keep track of that. So my purpose is to boil the water on the left-hand side. When I do that, what's going to happen, this is the small amount, is energy will be added that will not increase the temperature because at boiling, the temperature will remain at 100 degrees C, but it will increase the phase energy, and we can quantify that with this constant we're looking for, heat of vaporization, times the mass, which we could measure. It's about 5 grams. In the other beaker, because there's more water, the energy added will not cause a change in phase because it will never get up to the boiling point. Instead, the temperature will increase. And we can quantify the amount of energy that's added for a temperature increase by using specific heat times mass times the change in temperature. And we know specific heat for water, and we can measure both the mass and the temperature change. So two things are going on the same burner. One, we're increasing phase energy. The other one is that we're increasing the thermal energy of the large amount of water. And because they're happening to identical beakers on the same hot plate, it's reasonable to think that the amount of energy added into both beakers is the same amount of energy. So that means the two equations that we have here that quantify energy, well, they could be set equal to each other. We know the mass of the boiling water. We know the mass of the water that's being heated up or warmed. We know the temperature change if we measure it at the beginning and the end of the boiling, and we know specific heat, which leaves us only with heat of vaporization. So this water's been coming up to the boiling point as we've been waiting here, and it looks like it's just about ready to boil. I can see some fog starting to occur on the side of the beaker. And I'm starting to see some bubbles, so it looks like right about now 25.9 degrees maybe. We saw bubbles beginning to occur. And we're just watching water boil, so I'm going to speed this up. So the idea is we're just going to let this boil until all of the water has been boiled off. All 5 grams will have been boiled. And then we're going to monitor what happens to the temperature change of the larger amount of water, roughly 100 grams. getting to be less and less water in the left-hand beaker. And now it's almost gone. You can just see a little bit of water dancing around the bottom. Now even some of the fog is starting to disappear. And it looks like at this point, this water is completely boiled away. So I think it was about 57.1 degrees was the temperature when the water completely boiled. So now our objective is to use this equation that we established to find out what is the heat of vaporization for water. Remember, that's the only thing that's unknown in this equation. One thing we want to do is distinguish between these two kinds of masses in our equation. The mass of the boiling water, that was about the 5 grams, that was the smaller quantity, and then there's the mass of the water that warmed up. So I'm just changing the symbols here so that we can keep those straight. So let's solve for the value that we want, which is the heat of vaporization, delta H vap, by dividing both sides by the mass of boiling water. And this gives us an equation that we can just plug in our values and we can get our answer. The first thing we'll have to do is we'll have to figure out what is the delta T for the water that got warmed up. It seemed to me like it began boiling at about 25.9 degrees Celsius, and as best I could tell, it was 57.1 degrees Celsius when the water had just finished boiling. So that's the temperature change that the larger amount of water underwent during the time when the 5 grams of water boiled off. So the difference between those two is delta T, and that's 31.2 degrees C, and that's what we'll substitute in for delta T in this equation. 4.18 joules per gram per degree C is specific heat for water. The mass of our warm water, remember, was 100.08 grams. 31.2 we just calculated as our delta T, and the mass of the water that boiled off, remember, was 5.02 grams. If we combine all of the values in the top, we'll get one single number, and that's 13,100. And the unit is joules because grams and degrees C will cancel. So our delta H vap is 13,100 joules divided by 5.02 grams. Of course, in science, we never leave anything but a 1 in the denominator, so we'll actually do the division problem here. And so we get our delta H vap value as 2,600 joules per gram. There actually should be 3 significant figures there. So what we've just done is calculated the value of the heat of vaporization from experimental data. And the value that we got is actually exactly the value that is the accepted one that's used by scientists and engineers all the time, based on many experiments over the years. And we can use this value, 2,600 joules for every gram of water that gets vaporized, in predictions about how much energy is required or how much mass could be boiled away. It's the constant that we'll use in all of our problems.